Good morning. Thank you for picking this as your first talk, not counting the keynote. Today we're going to be talking about code quality metrics, which is something that's of great interest to us down at Sorcery. And we're going to be talking in particular about how to use and how not to use code quality metrics. So let's start off by talking about code reviews. Who here does code reviews? Who gets their code reviewed from time to time? Raise your hands. Yeah, that's pretty much everyone. Who does code reviews? Who code reviews for other people? Yeah, that's quite most of us here. Who's a solo developer and doesn't do any code reviews at all? Yeah, I thought it might be one or two. And who thinks their code reviews are objective? That's what I thought. So today we're going to be talking a little bit about how to introduce some objectivity into your code reviews in certain situations.
So for that, we are going to introduce some metrics, then try to then show how you can gain insights from those metrics. And we think it's very important to talk about the pitfalls of those as well. And I'm Reka, and my colleague is Ben. We both work at Sorcery on code quality tools, which includes refactoring automation and automated code reviews. So that's one of the reasons why we are so interested in this topic. And in the years before joining Sorcery, I worked at FinTech APIs.
And as I said, I'm Ben, and before joining Sorcery, I did a PhD in material science and then worked as a data analyst and data engineer at a fintech company. So throughout this presentation, we're going to be looking at a few code snippets. We're going to be doing some code review, in fact. And as we go, we're going to be normally left and a right, and I just want to get your initial opinion. And the reason for this is that these code quality metrics are sort of designed to mirror our personal biases, our personal feelings about what good code looks like. So when we see these things on the screen, I'm going to call out on the right, and let me know which one you prefer. Let's get started with the first one. Got two code snippets on screen, and without any sort of in-depth reading into what these do, who prefers the code snippet on your left, the one on my right? One person, interesting. And who prefers the one on the left? On my left, your right. Yeah, that's most people. That's kind of what we guessed. And when we talk about these sorts of pieces of code, we've generally got several bits and pieces that we might code. Things like whether it is Pythonic, whether it is elegant, whether it is short, whether it is flat. We talk about naming conventions. And all of these are very useful terms, but they fall into a bit of a region of difficulty if we're not thinking more specifically about how to apply those terms.
So to introduce very... all right. So to... sorry. So again, a very similar question to the previous one. Please take a look at these code 2 snippets and raise your hands if you prefer the one on the left. And please raise your hands if you prefer the one on the right. And probably the reason is that the second one is significantly shorter, which introduces our first very simple but surprisingly useful metric, functional length. And here we counted the statement in these snippets, but in Python it's even simpler to count the lines, which is often very close to the number of statements at least. And this can already give us some good feeling about how complicated the code is. So if you come to the conclusion after this talk that the other metrics are way too complicated, not worth the hassle, that is already a way to make your conversations about code a bit more specific and a bit more numeric. And one thing which functional length has in common with the more sophisticated metrics, that it definitely has its limitations, and as this one single statement shows, it's not always a good thing to strive for the shortest possible solution. So this introduces the next a bit more sophisticated quality metric. Which snippet do you prefer from these two? Please raise your hands if you like more the one on the left. Thanks a lot. And raise your hands if you prefer the one on the right. Thanks. And here the difference isn't in size, but rather in complexity, which leads to our next metric.
Yeah, so we all know the danger of one-liners. And this next metric is a way of sort of overcoming some of the difficulty in describing code in terms of shortness. Cyclomatic complexity is essentially a measure of the number of branches in your code. There's a more mathematical description, but we don't really need to get into it. The right here shows has 7 branches, and by a branch we just mean different routes that might happen through the code depending on the initial conditions. And the one on the left, the sort of intuitively nicer one, nominally only has 1 branch. Now I've put because in practice it's obviously more than one initial way through this code, but the cyclomatic complexity was developed quite some time ago. The calculation's simple. For every if statement, every try except block, and there's a few other conditions as well. We just add 1, and that is the total cyclomatic complexity of the code. As I said, this was developed quite some time ago, back in the 70s, and it was this would be great. There you go. At a time when code was significantly more monolithic than it is today. This is a famous photo of Margaret Hamilton with her code for the Apollo 13 program, when testability and maintainability were really important. And testability in particular is closely related to cyclomatic complexity. The more branches you have in a piece of code, the more things you need to test going through it. So that was why it was developed and why it's still hanging around. It is quite useful just as that first guess of how do we go beyond function length. But it too has its limitations. These two pieces of code are a bit more similar than ones but just as, again, rough intuition, who prefers the one on my right, on your left? And who prefers the one on my left, your right? Yeah, so that leads into the development of cyclomatic complexity into our next metric.
So, and this is called cognitive complexity. Both of these snippets have a cyclomatic complexity of 3, but the major difference is that on the left we have a nested structure, and on the right we have exactly 3 top-level branches. And this is something which cyclomatic complexity doesn't make a difference of, but cognitive complexity penalizes not just new branches, but every nested structure, which gives this very short snippet a cognitive complexity score of 8. And cognitive complexity was developed as an improvement of cyclomatic complexity. And one significant difference between the two metrics is the nesting, which we have just presented. Another one is that it also penalizes recursion. And on the other hand, it tries to incentivize good coding practices, things which it calls shorthand structures, which summarize multiple lines of code in one. And this is something where Python really shines, for example, with list comprehensions and context managers. And cognitive complexity is much newer, so it was developed in 2016, and I encourage you to check out the Sonar's paper, which has been updated since then regularly. And in the introduction, they mentioned that cyclomatic complexity does a good job of providing testability, especially branch coverage, but maintainability is a different thing, which has a lot of other components. And one thing which they put a lot of emphasis on is readability for humans, and that's why, for example, nesting and recursion are regarded as not so great features. Of course, cyclomatic and cognitive complexity both have their limitations as well, because here both scores for this snippet would be 1, but probably you still wouldn't describe this as really readable.
So to motivate our next metric, we're going to do a little exercise here. It's not code review. There are 3 numbers on screen, and the next slide is going to be blank, and I'm going to ask you to put your hand up if you'd feel confident remembering these 3 numbers. Hands up. Good. I'd expect nothing less. 7 numbers on screen now. Going to give you 3, 2, 1 to remember. Who would feel confident remembering those 7 numbers after that? Yeah, okay, about half people. That's kind of what we'd expect. You can see what's coming next. 2, 1. And who'd feel confident reciting out those numbers? I think there's 13 there. No one. Interesting. We'll come back to that in a sec. Oh, well, that's cheating. So this is a very well-known psychological phenomenon. It's difficult to keep more than about 7 things in your brain for short periods. So this motivates our next metric, which we call working memory. And this is a very much work in progress thing that was developed down at Salisbury by Brendan and Nick. So there's a number of ways we could describe the calculation for working memory. This is the one I've chosen for this talk. The essential idea is that for each statement we look at the number of variables in use, we look at the number of variables which are no longer in use, but you might need to keep in your brain to work out what's going to happen. And we also add an additional penalty for conditions, because the context matters, basically. As we work through a function or something, we look at the peak cognitive complexity, and we use that to describe, the peak working memory, and we use that to describe the overall working memory of that piece of code. And as I already mentioned, this is based on the sort of 7+2 rule in psychology. Now, you might sort of think, well, I don't need to remember everything. And that's 100% true. It's one of the major limitations of the working memory as a metric. For instance, if you knew that these numbers we just looked at were part of the digits of pi, you might have a much easier time reciting or being confident about those last few numbers. Does anyone know pi to sort of 25-ish places? Yay. So this is, as I said, one of the main limitations is it's very difficult to specify what people need to know as they're reading code. Do they need to remember the elements of the standard library? Do they need to remember the context of the package that they're working in? There's a sort of element of expertise that comes in here. So it's subjective and it's a bit difficult to define, but it is quite well rooted in psychology and in code style, as we'll see in a bit.
So we have just seen 4 different metrics. 2 of them were trying to measure the size of a code snippet, and 2 of them the complexity. And for both, we have a human-focused and a code-focused view. And what this small matrix is trying to show us that it's not that one of those is necessarily better than the other, but these are all important aspects of readability. And it really makes sense to try to improve all of them. So to shorten your functions and aim for conciseness, to reduce the cyclomatic complexity and create specific methods which don't have too many branches, reducing a cognitive complexity by nesting those branches, also following the Zen of Python, and also reducing the working memory by being conscious about the scope of the variables we introduce. And we have already seen 4 metrics, which sometimes perhaps contradict each other, and sometimes it would be perhaps nice to have one single score showing whether a code has gotten better or worse. So at Sorcery, for example, we use a weighted average for this, and another very interesting attempt for this is the maintainability index in PyCon 2019. There was an excellent about this from Anthony Shaw. So if you are interested in metrics generally, I encourage you to check out the video about that.
So let's take a look at some ways we can measure some of these things for real repositories. So here I've got a type of chart. This is called a box and plot. If anyone's familiar with Seaborn, you may have played around with this. Box and plot is basically a sort of discretized distribution. It's one way of, it's an extension of a box plot, essentially, and each of the boxes corresponds to a quartile. And what we're looking at here is the function length for all the functions in some of these repos. We haven't picked these for any particular reason other than that they are popular, they're well tested, and they're quite familiar to people. Notice on the bottom I've got a log scale, so these metrics on the far right are particularly long functions. We've got functions with well over 100 lines in them. There's a couple of things I want to draw your attention to. One is the line down the middle of the boxes represents the median. And what I found really interesting looking at this the first time was, well, the median of all of these, the median function length in all of these packages is approximately the same. It's between 5 and 6. And that just indicates, well, if we want our code to be maintainable, easy to use, open source stuff, aim for 5 to 6 lines in your function. That's a good style guide, and that's the thing that I want to draw from this. The other thing is, I already mentioned, there are serious outliers, and we'll talk a bit in a moment about why the outliers are important. As well as function length, we can look at the cyclomatic complexity, that's in blue, and the cognitive complexity. I've drawn these side by side because they're quite similar. The only thing I'm going to draw attention to beyond the last slide was, well, as we'd expect, the cognitive complexity is a little bit more than the cyclomatic complexity for most of these repositories, as we'd expect. The working memory, and this is something I alluded to earlier, again, the median of all of these repositories has an approximately equivalent working memory. And that's really nice because, again, it says, well, whether by design or happy accident, these functions have grown to have a working memory about 9. That's within the sort of, parameters of what we can keep in our brains. So it's a good indication that the psychology that was developed for the working memory metric is actually seen in practice, even without trying.
Another interesting way to look at these numbers is to compare the numbers of the same repository across time. And here we can see the cognitive complexity of a specific repository, so you can find some more similar analysis at repoanalysis.com. That here we just pick the repo which shows a pattern which is probably a bit typical. So we see cognitive complexity, so the lower numbers are better. And we see that this package started out with a fairly high complexity. Then around version 0.8, there was a big rewrite, which significantly decreased this complexity. And since then, there is a trend of sometimes going a bit up when new features are added, and then comes a period of refactoring and stabilizing where complexity goes down. This is the repository the only repository where we show where the data comes from because it is our own. And here you can again see the cognitive complexity, and it looks like quite good. So since 0.8, we have added quite a lot of new features, and the cognitive complexity has been still decreasing continuously. So everything nice. That's another representation of the very same repo, and it tells a little bit of a different story because we see that while the average complexity has been decreasing, we have also managed to add new outliers in this period, and I think this is a very general pattern which we tend to oversee, that even if we really care about quality and know how to try to improve it, we still add new outliers, and it means we add new technical debt.
Let's talk quickly about how to interpret code quality. And I'm going to draw an analogy with test coverage as another metric that we're probably quite familiar with. High test coverage, as we all know, doesn't necessarily mean that your tests are great. There's lots of ways that we can test things badly that nevertheless cover all of our code. However, it's important to note that low test coverage probably means your tests are pretty bad. And there's an analogy here with the code quality metrics. High code quality or good metrics, short functions, low cognitive complexity, that doesn't mean that your code is good. However, having high numbers of these functions probably indicates that your code is bad. And that's how we interpret some of these things. The higher numbers are less useful than the lower numbers.
So at the beginning we mentioned that these metrics can help us in various conversations about code, and one of these decisions is refactor or rewrite. So for example, let's assume that you are developing an application for an online conference and you need to handle time zones, and there is already some time zone package in your organization which has been used occasionally, and there is a discussion within the team members. Some of them say that yes, we obviously should reuse what we already have, while other team members say that, oh no, that code is quite difficult to understand, we are afraid that it contains some hidden bugs, let's just write something completely new. And this is the kind of conversation which has the danger of getting emotional pretty quickly, especially if the author of the library is involved. And we definitely don't say that this kind of a chart will give you an explicit answer, whether to refactor or rewrite, but it can give some good hints that, yes, there are many quite, so the majority of this library looks quite good, but again, we have some quite big outliers, and taking a look at these very complex functions is probably what should decide whether it's worth keeping working with this. Besides that, another decision where these metrics can give us some guidance is what to refactor and how to refactor. So regarding what, again, the outliers, like there's some functions with complexity around 70 there. So if you have something like a cleanup week or whatever, probably these are the ones where it makes sense to focus the most effort, and probably these are the ones which need the more additional test cases because they are the most probable to hide some bugs. And regarding how to refactor, usually these different metrics tend to correlate strongly with each other, so shorter functions are also less complex. And if there is a big discrepancy between them, that's often a sign that some specific kind of refactoring would be beneficial. So this is, again, an example from this repoanalysis.com, and this specific, in this module, the average function length is just under 3, but the average working memory is above 13, which is definitely above that optimal range. And this is an indication that we try to probably squeeze a bit too much information and too many different variables into those short functions. So in that case, we probably are missing some levels of abstraction, and we should introduce new data structures, new classes, something like that. So to summarize this section, it seems that there is a general agreement on some elements of good code style, like this median function length of 5.6, which Ben presented, and that keeping the working memory under 10 is the idea. It's very important to say that poor quality provides more information than good quality numbers, because good quality code can be still difficult to understand, so code with the good numbers can be still difficult to understand. And when you are doing such analysis, probably the most valuable information are the outliers, which show some areas for improvement.
Cool. So we've seen some ways that we can use code quality metrics, but the title of the talk includes a bit about how we should not use code quality metrics. So we're going to go through a bit of that now. One obvious problem with metrics in general is that they're typically gameable. We all know of ways that we can come up with, sort of systems to do code coverage, for example, that doesn't actually test anything. I heard a story yesterday of somebody who'd wrote a package which had 100% code coverage in their tests, but none of the tests contained any assert statements. This is the kind of thing that can cause a problem. We also really shouldn't be looking at using these types of metrics as developer performance metrics. They are biased. They sort of adhere to a particular style. And those styles aren't universal, and they certainly aren't necessarily applicable depending on the type of project you're approaching. We've also mentioned something about average code quality here. Averaging is a real problem for these types of metrics because, as we've already seen, they tend to live on a sort of logarithmic style scale. And the average, that dotted line on your far left there, that's way skewed low. The thing that we're most interested in probably is these outliers. So averaging, ranking, and sort of trying to use these things as developer performance indicators would, I think, become a real problem.
Besides that, it's important to mention that code quality contains some elements which aren't captured by any of these metrics. And here we see some examples for bad naming, like not so descriptive names and descriptive names, but not consistent terminology. Another important aspect is that these metrics are all quite on a short scale, so they measure functions or perhaps a module level, but they don't tell us anything about the structure of a project and also not about the external API of it and how convenient it is to use it.
So let's wrap up. We've seen a number of code quality metrics today. This is very much not an exhaustive list, but as we saw from the matrix, it does sort of tend to capture a reasonable subset of what we'd expect to understand about our code quality. So we've talked about the function length, probably one you already all knew about, things about the cyclomatic complexity, the cognitive complexity, and this idea of working memory.
And we have seen some areas where these metrics can provide valuable information. So they can be a good input to various conversations and trying to make them a bit more objective. They can also serve as code style checks, especially for things like method lengths or also like more complex things for working memory. They are a great way to identifying areas for improvement and pieces of the code which are most probable to have some problems and bugs. And they can also help us with some more complex decisions like refactor and rewrite.
We've been through the limitations of all of these metrics and also metrics in general. We certainly shouldn't be using code quality these metrics as the only measure of code quality. We should be very careful with our aggregations, and they shouldn't be used in rankings. There's one more final point I'd like to make, which is that, like everything, like a lot of the tools we use, code quality metrics are just a tool. You can't determine correctness using code quality, and that's the final line. It is a tool to help us write good. It's not going to tell us whether or not the code is correct and is doing the thing that it's supposed to do, and that's why we're all here. For those who might not be able to read this is one of my favorite XKCD comics, 4-star rating on an app, which has a good UI, doesn't crash, you can set multiple locations, but doesn't warn about tornadoes. Thank you very much.
So we would like to thank you to all the sources which you have used here and also to the developers of these various metrics. So you can check out these if you are interested in learning more about them, and you will find a list of these sources and some metrics about various open source repositories at repoanalysis.com. And you can contact us at the Sorcery booth number 713 or in the hallway here during the conference and at the GitHub after the conference.
Yeah, as I said, come and find us. We're happy to talk, and we're typically friendly. And we won't judge your code. Thank you.